Is Dennis Stanley from UWA talking about could an inexpensive, low-tech, low-energy, small-scale intervention that reintroduces normal mixing of the water column improve outcomes for corals during acute mass bleaching events?
Hi everyone, I'm a bit of an outlier talk in that I'm here to talk about ocean physics and look at how measurements that we've taken in the Great Barrier Reef and ocean physics and some computer modelling can all go in to inform what the vertical structure of the ocean looks like during bleaching events. And does this sort of acute stage of the thermal stress, could it possibly be relieved with some sort of mechanical intervention, or at least there's a resource of cooler water available? Okay. We'll start off just to get me going, more or less. This is a time series of the Moore Reef data logger during the 2017 bleaching event. So that's a daily average temperature of the logger. And the orange line is all the data available to that logger over approximately 20-year time period built into a climatology. Okay, so we can see the climatology of this logger versus what happened during 2017. If we add onto that chart those little red circles, those red circles are days where the wind speed was less than 3 metres per second, and the sort of not coloured in ones are 3.5 metres per second. So that's a doldrum day as defined by NOAA as a day when the wind speed is less than 3 metres per second. But what we can see is we can see strings of calm days in a row. We have this departure of the surface water from the climatology, right? And now if we put wind onto the same chart as well, okay? So the light blue trace underneath is the daily average wind speed, and the heavier trace is the wind speed from the last 7 days, right? And what we notice is that if we have periods of lasting high wind, then we get a return back to climatology. So we've got periods of calm days leads us to stretch away from climatology, and then periods of windy days brings us stretch back to climatology. And what's happening here is the ocean physics is that the sun's energy is coming into the water column. It's being delivered to the upper water column and it's heating that water. That water's becoming more buoyant and it gets trapped in the upper water column. What normally happens in the ocean is that turbulent processes, mostly driven by the wind, will stir this water back down and mix it through the water column. So if we have successive days of low wind, we get a hotter temperature day after day because the same energy is going in, but it's not being distributed through the water column. Ocean gliders, I operate ocean gliders, which is those little submarine-looking things on the front slide. We've operated them through the GBR for the last 5 or 6 years. And they do a complete profile of the ocean from the surface to the bottom every 5 to 15 minutes, depending on how deep the water is. And they do this 24 hours a day, 7 days a week. Okay. When you see our ocean glider data presented, it's often presented like this chart, and it looks like a continuous image, but it's not a continuous image. It's every one of those dots is a temperature measurement taken by the glider in the water at the time. So it's important to differentiate this from model data. This is really what happened, right? We can see the glider moving vertically through the water column, going up to near the surface and surfacing every hour, and the colour of the dot is the parameter being measured. In this case, it's temperature, and we can see the red areas are 31 degrees and the cool areas are 26 or something. Okay, so then if we put, this was the 2020 bleaching event that we captured really well with ocean glider data. And what you can see is, there are periods when that logger data goes above climatology, but you can see in the ocean glider data that above climatology water is concentrated in the upper water column, and the lower water column is correspondingly cooler, and that's important, right? Then we had an early arrival of the southeast trade winds in 2020, and that completely mixed the water column over just a couple of days, and the bleaching conditions were gone, okay? And we experienced subsequent recovery in 2020 and 2022. In the bottom frame, we don't have ocean gliders in all the time, and it would be lovely if we did, right? I've added E-Reef's model output to demonstrate to you that the E-Reef's model output resolves the same kind of ocean structure, because I'm going to extend this observation into other years using E-Reef data. Okay. We've had gliders in the water. We had a good period in 2022. So these are divided into bleaching years and non-bleaching years. In the bleaching years, you can see we measured stratification. In the middle one at the top in Cooktown in 2016. In 2017, we measured stratification in the Central GBR. In 2020, we caught the whole event. In 2022, we also caught and measured stratification. In the non-bleaching years, some stratification, but not for as strong and for not as long. All right. Because there's gaps in the data, we can present the same stuff with EREF's model output. And we see the same thing in 2016 and 2017 and 2020 and 2022. We see very strong periods of stratification that lasted a long time. Right? The other years still had periods of stratification. It's not an unusual event, but they just weren't as severe. Right? Now, if I only highlight the areas on this graph where the upper water column was hot enough above the coral bleaching threshold, something jumps out. And you see that it's only ever hot enough to bleach corals associated with stratification. Right? So it's only the upper ocean that suffers, okay? And it's a temperature distribution problem as much as it's an overheating problem. Now, I'm going to show a couple of animations now. And this is ocean profile data. So this is a plot of depth on the vertical axis and temperature on the other axis. So the top of the chart is shallow water, the bottom of the chart is deep water, the left-hand side of the chart is cold, the right-hand side of the chart is hot. And this is ocean glider going down, up and down the water column in the water at the time. We've first got a period of well mixed in 2022, and only about 10 days later, we have the onset of a bleaching event. Okay? So you can see the difference in the water column in the two animations. Okay? Oh, the icons at the top indicate day and night. Okay? So the vertical line indicates the whole water column's at the same temperature. This is a fully mixed water column. We can see the sun's energy being distributed, being entered into the surface, and slightly moving the line left and right. And then every night time, we see that fully mixed water column returning to a vertical line. The energy is going in and out of the water column, but it's acting across such a large volume of water that the temperature difference isn't very great. Right? We can see the effects of the turbulence. We just can't see the turbulence itself. That nightly reset to average conditions is important too. So now we're only about 10 days later, and we're going to see the evolution of a bleaching event. Okay? So we see that there's sun's coming into the surface, and there's a small mixed period indicated by the vertical line just to about 10 metres, but the mixing is only occurring down to about 10 metres. And that leaves every day to get successively hotter and hotter and hotter. What's interesting is the deeper water gets correspondingly colder and colder and colder. There's no change to the net heat content of the ocean. It's just that we've got the heat is concentrated in the upper ocean. And when I say no net heat contact in the ocean, I mean in the day-to-day basis. So we have these acute periods of coral stress that sit on top of the chronic degree heating style stress. And it's these acute periods that present opportunity to intervene. Okay, turbulence matters to coral flow, to coral bleaching. It's not just temperature. Low flow conditions sensitise corals to bleaching and reduce their chance of recovery. Right? So in low flow conditions, they stress, they bleach easier, and they don't recover as well. Tidal flow can support the flow that you normally get from turbulence, the wave action and stuff you normally get from turbulence. But if these events happen and they're coincident with neap tides, then corals are robbed of the flow they need to survive. During low flow conditions, there's less sedimentary suspension, so the water column's cooler, so the irradiance is higher. Right? And stratified conditions increase the upper ocean temperature. So this one parameter, ocean turbulence, ties together the bleaching conditions that we're all familiar with. High irradiance, low flow, and high temperature. Okay, we measured stratified conditions in 2016, 2017, 2020, 2022, and 2024. There is a resource here. If you have a coral garden or a local important tourism site that's undergoing bleaching, you can know that if you've got water that's 20 to 30 metres nearby, that's how far away the cold water is. It's not kilometres away, it's metres away, but it's just below, it's just underneath you. Right? So March 2020, I don't know if any of you remember March 2020, but there was a fair bit going on. And the global pandemic outbreak. But there was a sort of an unexpected bleaching event, and we got out there and we had already fabricated this pool model that we thought, oh, we'll give it a go out in the reef, and we wanted to prove two things. We wanted to prove the cold water was there and we could bring it to the water economically. This is not what you'd build if you were trying to solve a reef problem, but it's just a demonstration that the resource is there and you can get at it. Okay? There's a CTD cast on the left-hand side that shows you what the temperature was like during the day, just under 29 degrees at 20 metres, and at the surface it was just over 30. Okay, so we dropped a piece of ventilation duct down into the water column, and thus water driven through that pump was then drawn up from the bottom in the water column. Did I miss a slide there? Oh yeah, it was powered by a little tiny motor. We powered it by a little tiny motor because we had a point to make, which was you don't need much power. So that motor is about the size of a golf ball, and that's a small quadcopter battery. Okay. It was put in the water column, wound up to speed. We tested this in the pool to determine the operating point. At the sort of speed we're running at, it's delivering, which is half a metre a second, it's delivering 450 metres cubed an hour, right? And we did that with a motor that was a sixth of a horsepower, right? A tiny little motor. Okay, and we put a thermometer in the output to measure any changes. Okay, and we ran it for about a minute. The water was drawn up from the bottom. The temperature dropped. You know, it worked exactly as it was designed to work. Okay? So this sort of shows the low power and the low tech ability to reintroduce that cool water, or to reintroduce that mixing that's missing, right, and the turbulence that's missing. If you scale up this model just in energy, a 1 hectare tourism site to the depth of 5 metres could exchange all its water for 13 kilowatt hours, and that's about the same as a 10 horsepower outboard running for 2 hours. So it's not inconsistent with the sort of energy requirements that we're already doing on reef tourism sites. Okay? This isn't a highly energetically expensive exercise. Yeah, and I think, okay, so I'll let you just, I think, you know, the vertical mixing structure, the vertical column, water column displays a lot of variability, and within this variability there's opportunity. But yeah, if there's any questions.
Microphone on. Thank you, Dennis. We do have time for a couple of questions. Are there some online, Yvette? Oh, just you, sorry. Yvette's got a question for you.
The answer's no. Dennis, thanks heaps. I want to know, would it equally move water horizontally as well as vertically if you wanted to bring it from the outside of a reef to the inside of a reef?
Yes, you could. The bigger you make it, the more logistically complicated it gets. And I would imagine that the easier way to implement this initially would be to mix water, perhaps with a mobile system or something like that, but mix water that you know is going to be vectored onto your target reef. So you sort of move this thing around in order to mix water to move that's going to be vectored onto your target reefs. So at the right time of tide, you know, water will move that way anyway. My original thoughts were to build some sort of floating channel sort of thing that would direct the water horizontally. And it all becomes very difficult when there's wind and there's waves and there's water. But one of the implications of the work that we've done is that it's only really required when you've got these really calm conditions, right? So the difficulties in deployment might be overcome by the fact that if it's windy, then you don't deploy anyway because you don't need to, right?
Thank you. One more quick question? Yeah, Renata.
Thank you. So has this been trialled during bleaching, and does mixing cool water to the flats actually mitigate bleaching at all? Is there any evidence?
No, apart from there was modelling done that showed it was possible using the sort of devices that they use to mix reservoirs. I I think my role here is really to present the fact that there's a resource there rather than prevent the solution. I think the resource is that there's cold water available, and the universe of ideas has to apply themselves to that new resource that's available, and perhaps use it to relieve acute coral stress. And I'd like to stress that there's the acute component of it.
Thank you.
Okay, sorry, I think we might have to move on to the next talk, but thank you very much, Dennis.
Okay.
So next up...